water pollution remains a major environmental issue, harming marine life and disrupting ecosystems. To address this, our research focuses on developing the APBP Abyssal Explorer, an underwater robot inspired by nature, designed to explore and clean water bodies while minimizing environmental impact. The study aims to create an eco-friendly robotic solution that autonomously collects debris, navigates underwater using sonar and AI, and transmits real-time data. This project contributes to marine conservation and technological innovation.
Methodology for developing the APBP Abyssal Explorer began with creating a prototype to test its structure and design. A cardboard model was built to present the robot's design. The design of the prototype was inspired by marine animals to ensure smooth movement and minimal impact on the environment. Its orca shape reduces water resistance, allowing it to glide easily. Magnetic flippers and claws were added to grab waste, while sonar and echolocation sensors in its dorsal fin help it to navigate easily in dark waters. AI-driven autonomous communication transmit information to researchers through satellite communication. To keep the robot from threats, a defense mechanism was included, allowing it to release biodegradable ink like an octopus when needed.
Pseudocode, our APBP Abyssal Explorer, follows a structured process to clean the ocean and support SDG number 14. The system starts with activation, where the robot powers up using its hybrid solar and microturbine energy source. It then moves to exploration, navigating deep waters using AI, sonar, and echolocation to map the environment and avoid obstacles. As it moves, it performs trash detection, scanning for debris, while also assessing water quality and marine life activity. Once waste is identified, it proceeds to collection, where its magnetic flippers gather metallic debris while other tools collect non-metal waste. After collecting debris, the robot moves to resurfacing. Ascending to the surface, it then performs data transmission, sending real-time information to researchers via satellite communication. This data includes details on collected waste, water condition, and potential environment risks. Finally, it enters self-check mode, assessing its energy levels and system performance before diving again to continue its mission. This cycle ensures efficient ocean cleanup while protecting marine life. If the robot detects a threat, such as an aggressive marine animal, it activates its defense mechanism, releasing biodegradable ink to confuse predators.
Challenges and Solution. Building the APBP Abyssal Explorer came with many challenges that made us rethink our decisions. Cooperation was crucial, but the time constraint and miscommunication sometimes led to disagreements. Structurally, weak areas needed reinforcement to prevent bending or collapsing, and precision in cutting and assembling the prototype was difficult. Small errors caused misalignments, making the structure unstable and requiring adjustments. Since our prototype was made out of cardboard, representing sensors and moving parts accurately was another struggle, as the material was fragile and easily damaged. The robot itself has some functional limitations. While it uses solar panels and microturbines for power, deep waters with little sunlight and weak currents may reduce energy generation, limiting its operating time. Its sonar and echolocation sensors might also struggle in areas with strong currents or heavily pollution, affecting navigation. Satellite communication is another concern, as signals can be weak in deep sea trenches or disrupted by stormy weather. Finally, its defense mechanism has drawbacks. While the biodegradable ink confuses predators, it only offers a temporary escape, leaving the robot vulnerable if the threat persists. These challenges showed that the APBP Abyssal Explorer is a strong step forward ocean exploration and cleaning. There is still room for improvement to enhance its durability, navigation, and adaptability.
Discussion and conclusion. In summary, a robot prototype is a cutting-edge solution designed to support SDG 14 by addressing the critical need for deep-sea cleaning and exploration. It is built to remove ocean pollution from hard-to-reach deep-sea areas while also aiding scientific research by collecting valuable data on marine ecosystem. The APBP Abyssal Explorer shows how robotics and electronics can help clean the ocean in a smart and eco-friendly way. By using AI, automation, and renewable energy, this study proves that technology can be used to solve real-world problems like water pollution. This study also highlights the importance of working together and using new ideas to solve big challenges. The focus on sustainable design, clean energy, and smart ecosystem can inspire more improvements in underwater robotics. As technology grows, the research can help to lead better, more effective ways to keep ocean clean and healthy.
Building an underwater robot requires careful planning, especially when it comes to waterproofing and buoyancy control. Ensuring all electronics and motors are sealed properly with watertight enclosure is crucial to prevent water damage. The robot should also be neutrally buoyant so it doesn't sink or float uncontrollably, which can be achieved using foam, ballast tanks, or air bladders. Reliable propulsion is another key factor, with waterproof brushless motors and thrusters being ideal for smooth underwater movement. Additionally, communication must be considered, as radio signals don't travel well underwater. Using a tethered control system or acoustic signals can help maintain a strong connection with the robot. Material selection is equally important, as underwater environments can be harsh or corrosive. Using stainless steel, titanium, or specialized plastic will help improve durability and prevent rusting. If the robot includes a camera, a pressure-resistant anti-fog glass dome is necessary for clear vision. Testing in a controlled environment such as a pool before deploying in deep or unpredictable waters is essential to ensure all systems work as expected. By focusing on these factors, developers can create a reliable and efficient underwater robot for exploration, research, or other marine applications.